imaging in agriculture in a conventional sense, we need to start by preparing the required hardware, or this is how we do it. We go after preparing everything and tuning the hardware, we go to the field to capture images, then bring captured images back to the lab and process them using available software packages. A lot of times, this whole process can be done manually or automated. And a lot of times, after analyzing the images in the lab, we realize that we actually need to go back to the field and repeat the whole process because the quality of the pictures and images are not what we expected. And these days, for both image processing and data analysis, it's very common to use more advanced methods like machine learning and deep learning. A variety of platforms are available for imaging, such as conveyors, robots, unmanned ground vehicles, drones, etc. There's also different imaging techniques that we can take advantage of, such as RGB, NIR multispectral, hyperspectral, thermal, etc. And there's also another approach which calls multimodal imaging, and it's simply about combining two or more imaging techniques to be able to collect more information about a target. There are a variety of commercial cameras that are used in agriculture, and unfortunately, majority of them are actually designed and developed for industrial applications and they're not intended for agriculture, but we use them anyway because we don't usually have other options or any other option. This type of cameras usually have really high resolution. They can be very expensive. They come with high-level onboard image processing, and the manufacturers usually provide, a software package that these days can even, and some of these cameras these days are even deep learning enabled. And in general, they're easy to use, and you could say anybody can use them. There are many applications for imaging in agriculture. Such as monitoring of crop water status in real time, early detection of disease before visual symptoms are apparent, weight monitoring, precision livestock management, and so on. Personally, I have been mainly focused on plant water status monitoring by combining thermal and RGB or thermal and multispectral imaging. Despite all the interest and investment in imaging in agriculture, it's not easy to do it. And why? These are the challenges that I have personally also faced when trying to use imaging in agriculture. Affordable, reliable, standard hardware for continuous field monitoring are not available. The hardware, the camera hardware is usually not robust enough or waterproof to be used directly in the field, to be left in the field for continuous monitoring for extended period of time. One of the problems that I have personally faced is that it's not easy to keep camera lens clean if you can even manage to somehow protect it in the field. And they usually have type of cameras that are used really have high power consumption, which is a big challenge. Very frequently, we need to build a sensor suite for additional non-imaging measurements. And this is when imaging by itself is not enough. This happens very frequently in high throughput phenotyping. And changes in hardware might affect image processing and modeling needs. So when you assemble your own hardware, you use different types of camera to build a sensor suite. If you disassemble it and assemble it, this might affect, the hardware and consequently the image processing and modeling efforts that are previously done. In addition, sensor suites that are put together using different types of commercial cameras are really expensive, and they can also be complicated to assemble and maintain. There's also a need for multimodal imaging in a lot of applications in agriculture. A single imaging technique may not be enough. For example, we want to detect specific target leaf lesions in thermal images, and it's not easy if we only have a thermal image. So we need to. So one thing we can do is to create a mask using one imaging technique and use it to detect the target, and then be able to play with the thermal images better, in a better way. And when we use several cameras, it results in a complicated setup, and again adds to the expense. Imagine combining a $40,000 thermal camera with a $80,000 multispectral camera or a hyperspectral camera, and systems and setups like that. Another challenge in imaging agriculture is that imaging process in most applications is not automated. Images taken, so images are usually taken in the field, and as I explained in my second or third slide, that the field and then processed later in the lab. This might take weeks, if not months. And most of us are not familiar with image processing and computer vision. We're agriculturists, we're not computer scientists. Most commercial cameras provide unprocessed images. And most cameras do not provide feature extraction. So all the things that we need, they don't provide us with that. And image processing is not easy. As I said, we're not computer scientists by default. This is something we have to go and learn. Or if we don't have time to do that, we have to pay someone to do it, some expert to do it for us. And if you want to use convenient software packages, then we have to pay a lot more. So what is the solution? In my opinion, we need a hardware and software package that is designed and optimized for agriculture application. A package that we can develop it ourselves is a DIY. And we are familiar with every details of it. So those were the challenges that many of us have experienced. I have also experienced, but I'd like to tell you a little bit about my original motivation to develop such a system and use it. My original area of interest used to be precision irrigation for the most part. But over time, I realized that a reliable irrigation scheduling algorithm cannot only look at the water status. It needs to do much more. It needs to combine soil, microclimate, and plant sensors. So look at the soil, look at weather, look at the status of plants. It also needs to look at both biotic and abiotic causes of plant stress. But a lot of times they have very similar symptoms, signs. And we need to be able to tell the difference. And it also needs to rely on biophysical models. And so I'm not going to get into that for now. So I realized and I needed an all-in-one system. And such system simply did not exist. So I decided to develop it myself. So I started by developing an IRT-based plant water status monitoring system. That was the very first system that I developed. IRT is what I call it. Very often I call it a single pixel camera. But quickly I realized that that wasn't enough. Using IRTs, I realized that I had trouble separating, the canopy from the background. So I started using thermal cameras, and I did some developments there. But again, the type of thermal camera that I was using was expensive. So from thermal camera, I moved to using thermal modules, and I developed a system that was multimodal, combining thermal RGB, and actually in a project I mounted some of these imagers on a center pivot machine. Later on, I learned about other types of thermal sensors or thermal modules, and then I developed another system again, thermal RGB. Also developed a model of that, which was thermal multispectral, but this time I used another sensor called HEMA. And this one is my recent, or the last one is my most recent development, and it's a thermal multispectral imager. But it's in addition to imaging or thermal and multispectral imaging, it also relies on other types of measurement. It measures the distance from the target and other things. I will provide more details about it in the next slides. So these are the camera modules or examples of camera modules and sensors that I have been using for DIY, for to develop my systems. The thermal camera modules and sensors that are available in the market, commercially available in the market, and I have used some of them. They usually have low resolution when compared to commercially available thermal cameras, and the resolution does not usually exceed 120 by 160 pixels. They're relatively inexpensive. You can buy them for less than $300, but they don't come with any form of onboard image processing. Of theirs, one is very, very basic. And to use them, you need a breakout board, and you also need to develop your own firmware. And apparently, only hardware developers, software developers, can use this type of can use camera modules and sensors. Multispectral camera modules, they usually have a bit higher resolution. And here, when I say multispectral, actually majority of these modules that you will see in the market are RGB. They don't have an AR band. And if you want that, you need to do some modifications. So they usually have high resolution compared to thermal modules, but not as high as a lot of those commercially available. Again, cameras, multispectral cameras, the price can be really low. Again, they come with basic or no onboard image processing. Some of them might have more extensive image processing algorithms on board. And again, you need breakout board, and you need to develop your own firmware to be able to capture images and use them. And only hardware developers can use them. I've also been using microcontrollers and single board computers like the Raspberry Pi and BeagleBoard Plan to design my own systems. And as I said, that history, that background, those challenges brought me to the point that I decided to develop an all-in-one thermal multispectral imaging system, and I'm going to provide a little bit of details about it. So this is going to be a little bit kind of high-level, description of the system because of limited time. So the imaging system, this portable all-in-one multimodal imaging system is battery operated. It has a 7-inch touch screen. As I said, the Raspberry Pi single board computer has its core. I've added the UPS board, an interrupted power supply to support the Pi and have it perform more efficiently and better. There's an ultrasonic range finder integrated into the imaging system, which allows to measure the distance from the target, which can be a canopy surface. There's an incident light sensor, which can be used for automatic radiometric calibration, STI-12 port for to add an external sensor, a GPS receiver, and as I mentioned, the greatest thing about this imaging system is that it's multimodal. It combines thermal and multispectral imaging. The thermal module is a FLIR Lepton version 3.5 with a resolution of 160 by 120. And I added the thermal IR window for to protect the module from natural elements. I also developed, because the type of multispectral camera that I needed to develop this imaging system did not exist, I developed a multispectral module myself. And I use the CMOS. I use the CMOS RGB sensors. I did, as I said, modifying modifying the NIR filter that was there, and then I added an optical bandpass filter to create a multispectral module. So in this slide, you are seeing more. You can see more details or more hardware or more details on the hardware of the system. The part of this slide that I want to emphasize more is that, as you can see, the sensor, the peripheral sensors like a GPS receiver, light sensor, the circuit sensor, etc., are not directly connected to the Raspberry Pi. They're connected to a microcontroller. The microcontroller takes all the measurements and then sends them to the Raspberry Pi whenever ready. I personally believe this is a better way of managing the resources that the Raspberry Pi has to offer, and also it allows for a much better power management. I developed a graphical user interface that runs on board of the Raspberry Pi, and it's remotely accessible via the VNC Viewer app, so you can access it from your computer. So the imaging system can be, say, in a greenhouse in your lab, and then you can access it, from your office. I embedded certain crop models, the ones that I usually use, in the imager, in the software, and also some computer vision algorithms and for real-time image processing. So what it does is it's capable of doing automatic calibration of thermal and multispectral images, automatic image alignment and fusion, automatic target detection, and background removal or segmentation. You can use the imager in a manual mode, or you can do interval shooting by programming the imager to take images on its own. And if you do that, it would save images, raw images, and also export image features and models into a CSV file. So the imager, as I said, it has a STI-12. That is the STI-12 port. That STI-12 port allows it to pull data from a microclimate unit that is connected to the port. Here I used a Decagon MA 4100 microclimate unit, which measures air temperature, relative humidity, wind speed, and radiation. This is actually an older model of what now they call it Atmos 41 meter group. Both the name of the sensor and the company have changed. But yeah, it measures air temperature, relative humidity, wind speed, and radiation. And using other sensors that are embedded actually in the imager, it also measures canopy height. Of course, you need a reference for that. And then target surface temperature, canopy, and canopy cover. The crop models that I have embedded in the imager are a simple target, surface, and air temperature difference, delta T, a theoretical crop water stress index, or CWC, and I actually developed that model myself several years ago. Actual transpiration, stomodal conductance, and a crop coefficient. And using the microcontroller data, it also calculates reference ET and crop ET. So whenever the user captures an image or sets the imager for interval shooting, as I said, the imager runs these the algorithm that you see on board to process the image and then writes the results to a CSV file. So if I want to go through this very quickly, what it does is overlays chosen thermal and multispectral image layers. I will provide more details, and these images could be up to 3. Applies calibration coefficients to thermal and multispectral layers, does some image processing, and then creates an NDVI image layer, calculates delta TCW, CI, actual transpiration, etc. for every pixel, and then creates a thermal image layer that you can see that they can see it on the screen. Creates a mask for thermal and multispectral layers by segmenting the image, and then uses the mask to remove background from thermal and multispectral layers. And at the end, it calculates canopy cover, crop coefficient, and crop ET. Calculates center, average, maximum, minimum values for the thermal layer. And as I said, it saves raw and fused images and write model outputs to a CSV file. So let's get into more details and see how the algorithm works and how the software works. So the algorithm can overlay up to 3 image layers and then fuse them. Layer 1 can be a multispectral image. It can be a combination of all the available channels, bands, or red, green, and NIR, or individual bands. And then layer 2 is the index, what I call it, the index layer. It could be red NDVI, GNDVI, or whatever. Basically, the imager with the embedded functions and models is capable of calculating. And layer 3 is the combination of thermal and thermal data and microclimate data. And it could be delta TCW, CI, actual transpiration, etc. So the images that are captured by the imager are not aligned, and the imager needs to do the alignment or image alignment or image registration somehow. So there are 2 options available. So it can be done either manually, and the user needs to provide the target distance, or it can rely on an automatic algorithm which moves the pixels of one image over the other based on the distance data that is provided by the ultrasonic sensor. Yeah, if you check the reference that I have provided at the bottom of the slide, you can learn more about this method.